Here we are going to solve for the kernel and nullity of a linear transformation using these two matrices here. We know that kernel is a set of vectors V that will, under the linear transformation, will resolve to the zero vector. But what type of zero vector and what type of vectors V are we going to look for? Take note that we have here 3 by 2 matrices. This is also a 3 by 2 matrix. And if we have here m by n, meaning n is 2 and m is 3, we need to understand the type of linear transformation form here so that we could come up with the correct analysis on the zero vector and the vectors we are going to solve for. So the linear transformation of this is from Rn to Rm, where n is 2. In short, we have here R2 to R3. What is again the purpose of this? The purpose for this is that if we're going to look at here on our codomain, it's on R3. This would mean our zero vector is actually an element of R3. Hence, it's 0, 0, 0. It's not just any zero vector, but more specifically, it's a zero vector in R3. This R2 here is an element, is a part of our domain, and the set of vectors V are elements of R2. In short, the V that we're going to look for here is a combination of V sub 1 and V sub 2. We should not be able to interchange both of them, because if we do, we'll have different results. With that in mind, let us now start with solving for the kernel of the first matrix here. We're going to follow this process. The transformation of vector V is equal to the product of the matrix A with the vector V, as mentioned in R2, equal to our zero vector in R3. So it is actually better to really start with this. But first, let us come up with the reduced row echelon form of this matrix so that it will be easier for us to identify the V sub 1 and V sub 2, which comprises the vector V, or the set of vectors V that we're going to solve for. So here, we're going to copy 5, negative 3, 1, 1, 1, and 1. Let's multiply 1/5 to our row 1 for a new row 1. So we have here this form. Okay, you have here 1. This is negative 3/5, 1, 1, 1, and 1. If you don't like any fraction, of course, you can just simply interchange row 2 to row 1 so that we will have a leading 1 here. But of course, let me just continue this one here. As we move further, we are going to make these zeros. So to do that, we will have here negative of row 1 plus row 2 to have a new row 2, and also negative of row 1 plus row 3 for row 3 here will become 0. You have 1, that's negative 3/5 rather. So negative 1 times 1 is negative 1 plus 1, 0. So negative of 3/5 is negative 3/5 is positive 3/5 plus this. So you have 8/5. 8/5. Okay? Next, you're going to have here negative as well as this, plus that, 0. You also have here 8/5 here as well. Okay? Now, let's try to multiply 5/8 to our row 2 so that we will have here leading 1. So you have 1, negative 3/5, 0, this is now 1, this is 0, this is 8/5. Now to make this a reduced row echelon form, we're going to make these two zeros. So first, negative 8/5 of row 2 plus row 3. So this would be 0. And then we are going to have 3/5, positive 3/5 times row 2 plus row 1. So that this entry will become 0 as well. So you have here, of course, is 1, that's 0, 0. This is 1. 1 times negative 8/5 is negative 8/5 plus this, 0. 1 plus times 3/5 is 3/5 plus this, that's 0. So after here, this is now the reduced row echelon form. This will be used together with this process, multiplying a certain vector V in R2 and equating to R3, which is a zero vector in R3. This is to be multiplied with V sub 1 and V sub 2 equal to 0, 0, 0. You would also know that your understanding and analysis is correct when you're going to check this and the product is defined. Because if you're going to really say this has v3 because our vector is an element of r3, this is no longer defined because you only have two entries here to be multiplied with 3. So it's really correct to only have vector 2. So with this, we can just simply say v sub 1 is 0 and v sub 2 is also 0. Hence, the vector v, which could make our transformation here be equal to the 0 vector, is a 0 vector in R2. So the kernel of T is a set containing 0, 0, 0. And the nullity of this transformation is actually the dimension of the basis of the kernel. Notice here we have one element on our kernel of T, but since that element is a 0 vector, it has no basis here. In short, our nullity of T is 0. Nullity kernel of the first matrix. Moving on to our second matrix here. So same process. Let's try to come up with its reduced row echelon form. So you have 4, 1, 0, 0, 2, and negative 3. Let's multiply in 1/4 to row 1 so that we will have a leading, so that we will have a leading 1. So you have here 1, and then you have 1/4, 0, 0, 2, and negative 3. By the way, we can also interchange row 2 and row 3 because when we talk about reduced row echelon form, the row of zeros must be placed at the bottommost part. So 1, 1/4, this would be 2, negative 3, and this is our 0, 0. Then let's make this 0 by multiplying negative 2 to row 1 plus row 2 to have a new row 2. 1, 1/4, negative 2 plus a times 1 is negative 2 plus 2, 0. Negative 2 times 1/4 is negative 1/2 plus negative 3, that's negative 6 halves, so negative 7 halves. Okay, again, negative 2 times 1/4 is negative 1/2. Okay, then negative 6 halves, negative 7 halves. Okay, that's correct. And here, we're going to multiply negative 2 sevenths to our row 2 so that this would be a leading 1 as well. Okay, we have 1, 1/4, 0, this is now 1, 0, and 0. For this to become a reduced row echelon form, let's make this 0. So we will multiply negative 1/4 to row 2 plus row 3 to have a new row 3. So we have here 1, 0, 0, 1, 0, and 0. Same as earlier, multiply this to our vector in R2, equate to our 0 vector in R3. We will have the same values for v sub 1 and v sub 2, which are both zeros. Hence, the vector that will make the transformation equal to the 0 vector in R3 is the 0 vector in R2. With this, we'll have the same result here. The kernel of T is a set containing 0 and 0, and the nullity of T is 0 as well. Because again, if the element of the kernel of T is the 0 vector, we will not count it as 1 in our nullity. So we have these results. So this is how do we determine the kernel nullity of a 3x2 matrix under the linear transformation. Thank you very much for watching.